everyone. Today I want to introduce you a novel feature extraction technique for very high resolution remote sensing image based on adaptive compressed histogram attribute profile. My presentation has 5 main parts. The first part is introduction, the second part is aim of my thesis, and then proposed feature extraction technique, and then experimental result, and final conclusion and future development. Now moving to introduction. Nowadays the available of very high resolution image for remote sensing requires effective method for extracting the spatial information from the image. Several techniques have been introduced in order to solve this problem. Among them, monophysical attribute profiles is quite effective by applying the sequentially attribute filter to extract the spatial information. However, the use of attribute profile can be insufficient if the complex texture information is present in very high resolution image. So histogram attribute profile is recently introduced in order to overcome that. You can see from the original image, after applying the attribute filter, we have a stack of filtered image, and then we estimate the local histogram for the X pixel, and finally we stack them into one texture descriptor vector, and then use it descriptor for classification. However, the performance of histogram attribute profile is quite good, but it can be very high dimensional. So we face to the problem of the cost of dimensionality and the storage requirement. So uniform quantization based compressed histogram attribute profiles are introduced to overcome that. Here, instead of stack the local histogram in the texture descriptor vector, here we put it, we accommodate it in the 2D texture descriptor. We can see each row of the descriptor represent a histogram thing, and each column represents the local histogram, the sample. And then after we have the 2D matrix, we divide it into the blocks, rectangular non-overlapping blocks, and then each block are characterized by the sum of all the frequency inside the block, and then we stack all of the sum into the new compressed texture descriptor and use them to classification. However, because the spatial information are not uniform distributed, so we face to the problem of lost information. And selecting a proper window size is often a difficult task. So it's simple, but it provides suboptimal performance. So my aim of my thesis is provide a complete and detailed characterization of spatial information, while optimize the number of features that present in the image information, the storage requirement, and the computational load in order to overcome the very high dimensionality of histogram attribute profile and the limitation of uniform quantization based compressed histogram attribute profile. So here is the proposed feature extraction technique. It has 3 steps. The first step is the characterization of histogram attribute profile by 2D descriptor, as I mentioned above. And the second step is the feature extraction from 2D descriptor by compressing the redundancy. This has 2 substeps. The first substep is inter-class and intra-class redundancy analysis, and the second step is the compression of redundancy and extraction of the feature. And final step is classification. Moving to inter-class redundancy analysis. To perform this analysis, a 3-step strategy is used. The first is 2D class descriptor are obtained by calculating the average of 2D descriptor among the training samples are labeled under the same class, and then obtain the interclass difference matrix, and then final interclass redundancy of a matrix. Here is an example. First, we calculate the 3 descriptor for class 1, 2, and 3. You can see, and interclass different matrix is actually the absolute value of differences between 3 descriptor. For example, here 1 vs2 interclass different matrix is actually get by the absolute value of difference between 3 descriptor for class 1 and class 2. Here we get all the interclass different matrix. And finally, the interclass redundancy aware matrix is obtained by all of the position of this matrix. Actually, the minimum of the interclass difference matrix which is the same position. For example, the red one is 2, is the minimum of 5, 2, and 3. So the interclass redundancy aware matrix help us to estimate how the redundancy between a pair of classes. Moving to intra-class redundancy analysis. To perform this analysis, characteristic vectors are obtained for each feature. You can see here, for example, the characteristic vector for the position 1, 1 is 2, 7, 4. It's the red one, 2, 7, 4, and for the position 1, 2 is 3, 5, 0. It's yellow one. So I use the Chebyshev distance for estimating the similarity among the features. The Chebyshev distance is actually the maximum of difference between features. Now moving to the compression of redundancy and feature extraction. Here's this step is the 4 main substeps. The first step is dividing interclass redundancy aware matrix into blocks, and then choosing the block representative entry, and then for each entry choosing the most similar block representative entry and assign a group label, and then sum all of the entry within the same group. For example, you can see an example here. Here is the interclass redundancy aware matrix. First, we dividing it into the block, and then for each block, we choosing the feature where we get the maximum value of this matrix. Here I color it, and then we choosing the most similar block representative entry for each of the rest. Here, in order to find the block representative entry, we can first using the exhaustive search. Exhaustive search means we consider all of the block representative. But if we do that, we face to problem of computational complexity, and then because here we face to the problem of impulsive problem. It means that when the training sample you choose is not so good, we can mistake. We can have some error on estimation the similarity between features. So I introduce the neighborhood block search. It means we only consider its out block and its neighborhood block, its adjacent block. For example, let's consider the bottom left feature, and for choosing the most similar block representative, I only consider the blue, the violet, the black, and the yellow one, because it's adjacent block. Another block I don't consider. Then moving to experiment result. For experiment, I used the panchromatic image of Trento from July 2006 with the resolution is 0.6 match. Two test sites are available is Trento 1 dataset and Trento 2 dataset. Numerous higher building from residential to industrial one is considered, and foreign cover glass is the road building, shadow, and vegetation. In order to use attribute profile, I use area, standard deviation, and moment of interior attribute filter. And the result will compare with the original histogram attribute profile and uniform quantization based compressed histogram attribute profile. I'm using support vector machine and histogram intersection kernel. Using five-fold cross validation approach. Moving to the result for Cento dataset 1. You can see the proposed method can very effective, get 93.4% of accuracy with the feature length is only 13. Compared to the original histogram attribute profile, can achieve only 97% accuracy with 392 features. So the compression ratio is really high. Here we can see the classification map. You can see the proposed method can actually get very similar classification map with the original one, and when reducing significantly the computational complexity. And here's the experimental result for the Cento 2 dataset. The same thing happens. The proposed method can get 87% of accuracy with only 24 features. When compared to histogram attribute profile, the accuracy only 78%, with the feature length is 294. And here we can see that the neighborhood block search actually outstanding the exclusive search in compared to the accuracy of the feature length. So, as I mentioned before, the active search, when we using the exclusive search, we face to the problem of eco-snip. It means that the training sample are chewing is not so good. And here the classification map for Cento 2 dataset, the proposed method is that very similar to classification map for the original one. And now moving to conclusion and future development. So now I introduce the proposed methods introduced. We can see that it can effectively compress the redundancy information in histogram attribute profile. It can provide a complete detailed characterization of the spatial information. And it highly discriminative, it optimizes the story code and easy to compute. So after feature development, the adaptive distant neighborhood block search will be developed. Thank you for your attention.
Maybe one or two questions. So regarding the intra-class matrix, dependency matrix. So can you explain us one of these slides? What does each cell of one of these matrices represent? So for instance, if I take cell 1, the first cell, what does it represent?
Sorry, what?
For instance, take the first cell, 2, that number 2. No, the matrix, the first matrix.
Okay, here.
Yeah, the first cell. For instance, that one. Okay, anyone, any cell. So what does the number in any of these cells represent?
Actually, here is the frequency, because it's with we do with histogram attribute profile. So it's the frequency, the local.
It's the frequency of what? So, for instance, the first cell we are computing the frequency of what?
Okay, I mean, here after we from the original image, we applying the attribute filter, and we have the filter image. And then for each pixel, we estimate the local histogram. For example, in my thesis, I do the window size is
okay. You have the local histogram for each,
yeah. And then here is the class you asked about, the 2D descriptor, class descriptor. It's obtained by the.
So does it mean that in the matrix?
It's obtained by the calculating the average of the training sample, all of the training sample under the same classes. By average.
So the size of the matrix, is it related to the number of bins that you extract?
Yeah.
The
histogram bin and the.
That's fine. Just a last question. So since you are computing the intra-class redundancy,
yeah.
Does it mean that you need a spatial ground truth? That is, we need to compute this matrix on each polygon of each class, or not?
I mean, here I always calculate the differences between the two class descriptor. This means that, for example, here when the distance between classes is high, this means we more easier to classify the classes.
Okay, that's fine.
I have a curiosity. Are there, I mean, usually you evaluate and you show the nice results. So I'm curious about whether there are cases of images where these would perform poorly and potentially even worse than the original methods. I don't know. Very uniform pictures or very blurred, or you know. Is there any limitation to this method? I guess this is the question. It's a tricky
Because
question.
I use the compression. So here, for example, you can see that here's the accuracy when I increase the number of the x-axis feature. So you can see that if the x-axis feature is not so high, the result is obviously cannot hide. But for example, in the reality, in my experiment, if the feature length is is large than 20, the accuracy is normally good.
Thank you.